So we're in section 11.1, and we're talking about solid shapes and cross sections. So the first thing we want to do is talk about some terminology and the words we're going to use to talk about solid shapes. Before we do that, let's remember when we had a shape in the plane, so a two-dimensional shape, and the sides were segments. So we had the straight sides. And remember what we called the general word we used for that shape? What is it? Polygon. So we called them a polygon. In 3 dimensions, for our solid shapes, we're going to call them polyhedrons. So kind of the same. A polyhedron is going to be a solid, and our book calls them a space figure. Or a 3D figure. So a polyhedron is a solid, space figure, 3D figure that is made by parts of intersecting planes. So we're going to take these planes and they're going to intersect, and we're going to turn that into a solid shape. So the parts where they intersect are going to be our solid shape. That's going to be our polyhedron. The parts of the polyhedron, we call the sides of the polyhedron the faces. So the faces, whatever the sides are faces. The faces of a polyhedron are always polygons. Faces are polygons. So the stuff that we've learned about polygons already, we're going to use when we start talking about polyhedrons. So for example, all of the area formulas that we learned in chapter 10, we need to use the area formulas to find the volumes and surface areas of these solids, because the sides, the faces, are polygons. And everything that we learned about not everything, but we learned about how to find areas of polygons in chapter 10. So our faces of our polyhedrons are polygons. The faces intersect at edges. And the edges are segments. And then the edges intersect at vertices. And our vertices, we can think of the vertices as the corners or the points. The vertices are points. So we have our faces made of polygons, our edges are segments, and our vertices, the corners, are points. So if I sketched a polygon here, I'll sketch a really easy one. So just really quickly, a quick way to make a pyramid, sketch a little parallelogram, and then I put a point up here and connect the corners to that point. And there's my pyramid. So that would be a polygon. The faces around the sides are triangles. The face at the bottom here is a rectangle or a square for this particular one. So that would be an example of a polygon. And we have vertices at all the corners, and all these segments that I drew would be my edges. So we're going to learn all about how to find the area, the surface area of polygon or polyhedrons. We're going to figure out how to find the volume of different kinds of polyhedron, and we'll talk about some other shapes. We'll talk about spheres and cones as well, which aren't polyhedrons because their faces aren't polygons. All right, we will also talk about a regular polyhedron. A regular polyhedron has congruent polygons as faces. So all the faces of a regular polyhedron are congruent polygons. So what would be the easiest, the simplest regular polygon that we could think of? A cube. All the faces are squares, congruent squares. So a cube is a regular polygon. That would be an example. All right, so let's look at some examples. Well, let's look at an example talking about the edges and the faces and the vertices of a polygon. And then it turns out that there's a nice relationship between the faces, edges, and vertices of any polyhedron. So let's look at a quick example. So I want to do we'll sketch this polyhedron. And we're going to call this R, U, S, and T. We want to name the vertices, the edges, and faces. So let's name the vertices first. So what are the vertices of this polyhedron? R, U, S, T, just the points. So we just have 4 points that are the vertices. How about the edges? What kind of thing are the edges? Segments. The edges are segments. So we just need to name the segments. So what are the segments here? RS, RU, RT, TS, TS, SU, UT. All right, so we have six edges. And the faces. What kind of things are the faces? And what kind of shape? Triangle. So triangle RTS. Triangle RSU. RTU. And one more. TSU. So this one down here flies. So those are our faces. So we have 4 faces. So for this example, we had our faces were triangles. The edges are always segments. The vertices are always points. We can have all kinds of different shapes for the faces. Well, let's talk about the connection between the vertices, the edges, and the faces. So very famous, probably one of the most famous mathematicians ever, Leonard Euler, came up with this formula. And we've heard his name before. We talked about the Euler line in a triangle. But Leonard Euler was able to prove this relationship between the vertices, edges, and faces of a polyhedron. So for any polyhedron, doesn't matter how big, how small, how many faces it has, what the shapes of the faces are, as long as it's a polyhedron, our formula is F plus V equals E plus 2. F equals the number of faces, V equals the number of vertices, and E equals the number of edges. So it's pretty amazing that the relationship between the faces, the vertices, and the edges turns out to be this nice simple equation. And what it really tells us is how, in order for these things to connect up, in order to make a solid shape, really telling us about what has to happen for that to work. So let's look at this for our previous, from this example. So from before, we have V equals 4, F equals 4, and E equals 6. So I plug that into the formula. 4 plus 4 equals 6 plus 2. So for this polyhedron, we were able to verify Euler's formula. And what Euler's formula helps with sometimes, if you know how many faces and vertices or faces and edges a polyhedron has, you can use Euler's formula to figure out the other missing part. What's left. All right, questions so far? Okay, let's look at an example of where we use Euler's formula to figure out a missing part instead of counting. So let me draw a solid shape here. We're going to kind of stack two pyramids. We're going to make a solid shape by putting a pyramid on top of a pyramid, connecting them at their bases. And I'll make this line about, I guess this one. So there's my solid shape. So I took two pyramids, put them, the square parts together. So that's my polyhedron. And let's say we know that F, we know we have 8 faces and we have 6 vertices. So our 8 faces are the 4 triangles here and the 4 triangles here. 8 vertices we have, 6 vertices, we have the 4 around here and 1 on each, on the top and the bottom. We want to use Euler's formula. To find the number of edges. So instead of trying to count the edges, we want to use Euler's formula. Well, the Euler's formula tells us that F plus V equals E plus 2. And that's true for any polyhedron. So I get 8 plus 6 equals E plus 2. 8 and 6 is 14. Subtract 2 from both sides and I get E equals 12. So this polyhedron would have 12 edges. And it wouldn't be hard to count the edges, but we just wanted to use Euler's formula. All right, questions there? We can also use a form of Euler's formula in 2 dimensions. So when we're talking about a flat shape. So we're going to talk about Euler's formula for a net. And let's remember when we're talking about a net for a solid, for a net for a shape, what are we talking about? Yeah, we take it and we kind of cut it along the edges and lay it out flat. So if we folded it up, we'd get the solid shape. So we're taking that solid shape and laying it out flat. Well, Euler's formula, we can come up with a version of Euler's formula for nets. It works, so we're talking about a two-dimensional shape. So for the net of any polyhedron, Euler's formula in two dimensions, we get F plus V equals E plus 1. And for this one, we're saying that F equals, the book calls them number of regions. And by regions, they mean we're just going to count the polygons. So when we fold our shape open, we get a bunch of polygons connected to each other. V is all the vertices. And we're counting each corner. And E equals all edges. So we're counting each segment. And the reason this turns out a little different is because when we fold open a net, so our net, when we have it laid out flat, when we fold it up, some of the edges come together and the corners come together to be the vertices. So we're counting some of the vertices and some of the edges in a net more than one time compared to how we would count them with the solid. So that it turns out that the relationship there makes our formula turn into F plus V equals E plus 1 because we count some of the vertices multiple times and we count some of the edges multiple times. So that's how it works out for a net. So let's look at this formula in two dimensions. Let's draw a net for a cube. So if I cut a cube open, and I know my net is not going to be, my sketch isn't perfect, so I get the sides that make the squares that make the sides of the cube. So if I fold that up, I get the sides of the cube, but not the top and the bottom. So let me put a top and a bottom on here. So that we could fold over and make the top, and that we could fold over to make the bottom of my cube. And we want to verify Euler's formula for this net for a cube. So our faces, we're just going to count the number of polygons. So all of our polygons here are squares, so I have 1, 2, 3, 4, 5, 6. I have 6 faces. Our vertices, we're going to count all the corners. So I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. I've already counted that. So we have 14 vertices. And edges, going to count all the segments. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. And we want to verify Euler's formula. So Euler's formula says F plus V equals E plus 1 for a net. So I get 6 plus 14. Does that equal 19 plus 1? 20 plus 20. So we've shown that Euler's formula works for this cube. And it turns out Euler's formula, we can use it for polyhedrons, we can use it for nets. We can also apply Euler's formula to, it's used a lot in a branch of math called graph theory. where we talk about how things are connected on a graph. We can talk about the edges and the regions and the vertices of a graph, and it has to this equation has to work on a graph. So in for example with maps, it turns up in networks where you're trying to connect things in a network. Euler's formulas works for certain types of networks, so it shows up in a lot of different contexts, not just about solid shapes. So Euler's formula turns out to be a really nice thing and a fairly important thing that shows up in a lot of different areas. Kind of a nice little relationship that Euler came up with. All right, questions so far? All right, the last thing we need to talk about today are cross sections. And this is one of my favorite things about solid shapes, is just how we visualize them. Cross sections are, we're talking about slicing a solid with a plane. And we're interested in what shape gets traced out when we slice the solid with the plane. So for a cross section, we're slicing the solid with the plane, and we want to know what shape gets traced when we cut that solid by a plane. So let's take a look. Let's look at a couple of examples. Let's visualize some cross sections. So let's start with a cone. Cones are nice. So there's my cone. What shape would we get if we took a plane and we cut right through the middle of this cone, slicing right through the vertex, and we're cutting just like a screen cuts through that cone? What shape would we get? Triangle, right? So I'm taking a plane here, draw my plane in red, and we're cutting it. We're taking like a big guillotine, and we're slicing right down through the middle of that cone. And when it cuts through the cone, it's going to cut right through there. It's going to cut right through the middle of the bottom, and it's going to cut right through there. So our intersection would be, thank you. Our intersection would be that red triangle. So that would be the cross section. That would be the cross section when we slice the cone with that plane. Would be a triangle. What if we slice the cone? So here's my cone again. What if we sliced it with a plane going this way? So our plane is here, cutting through. And we want not what's left over, but what shape gets traced out just by the place where they intersect, where they meet. So we're not talking about the leftover shape. We're talking about just what gets traced out by where the plane and the cone meet. So if we cut through this cone, when we get something like that where we cut through, and if we turn that and we took that and looked at it straight on, what shape would that be? What is it? Circle. It would be a circle. So we're talking about just this piece where the plane cuts through, not the whole shape that's left over, just this piece where it cuts through. So our intersection would be a circle where that plane cuts through the cone. How about if we took that cone and the same kind of idea, but we cut through, our plane cuts through at an angle. What kind of shape would we get then? What is it? An oval. So the plane would cut through and we'd get a shape like that, right where it cut through. So we'd end up with an oval shape. And this shape is called an ellipse, and you'll learn about ellipses later. How about, see if we can visualize. We're going to take the plane, and we're going to cut the same way, but not cut right through the middle. So let's say we just take our plane and we cut just a piece of that cone off, but we don't go right through the middle. So what would we get there? We're cutting just a piece off of the side of the cone. Any idea? You end up with a shape that looks like kind of an arc shape. So where the cone cut through there, we'd end up with an arc shape, so kind of like that. And it turns out that shape is a parabola. When we cut through one side of the cone, we end up with a parabola. We have a circle, an ellipse, and a parabola, and these are called conic sections. You'll learn about conic sections in Algebra 2 and in pre-calculus. Questions there? All right, let's look at for our last one, let's think about a cube and what kind of cross sections we could get if we cut up a cube. So here's my cube. Now the book will ask you to sketch a cross section, and it's asking you to do just exactly what we did on this last page. Just take your plane, it cuts through your shape. What gets traced out when you cut through there? So what if we cut through the square with a plane that was going just like the screen? What if we took a plane like a knife or a guillotine, and we cut through that square? What shape would we end up with? Cut through right through the middle. Right there. If we could end up with if we cut right through the middle, and we'd end up with a square. If we cut right through the middle, we'd end up with a square. And remember, for the cross section, we're not talking about the solid pieces that are left over, just what gets traced out as we cut through. So we'd end up with a square. So we sliced straight down, we'd end up with a square. What if we sliced at an angle? So here's our cube. And we're slicing through now, like so, from here to here. And it's going straight down here. So we'd end up with a rectangle. That would slice straight down there. And we'd end up with a rectangle. What other shape could we end up with if we cut a cube with a plane? Could we get a triangle somehow? How could we get a triangle? What if we just cut a corner off? What if I slice this corner off at an angle? Then we'd get a triangle. I'm having a hard time drawing that last. There we go. So if we cut that corner off, so we're going at an angle sideways and down, we'd end up tracing out a triangle. So that little shape there would be a triangle. And if we went straight down, on one corner, we could end up with a rectangle kind of in a different way. So we could cut this entire corner, thank you. We could cut that entire corner off, and we'd end up with a rectangle going that way. So when the question asks you to sketch a cross section, it's asking you to do basically what we were doing here. Just think about how the plane's cutting through there and what shape gets traced out as you cut through. Questions on cross sections? All right, that's all we had to talk about today. Tomorrow we will talk about finding the volume. We'll talk about some special kinds of polyhedrons. We'll start talking about special kinds of polyhedrons. We'll talk about how to find the surface area and the volume of different kinds of polyhedrons and different kinds of solid shapes. All right.